In this video, we're going to look at how halides act as reducing agents, but in the first slide, I just want to talk a little bit about how the halogens act as oxidizing agents, just to recap it. So I've just quickly drawn the halogens and drawn on so that you can see that as we go down the group, you get one more shell each time and they get bigger. Now, if we consider what makes a good oxidizing agent, they're going to have to be really good at removing electrons from another species. So what factors are going to make them really good at being oxidizing agents? It's going to come down to their size. It's going to come down to the nuclear charge. Now, all of these are group 7, so in each of their periods, they're going to have the highest nuclear charge. But as we go down the group, the atoms get bigger, and therefore their electrons that we're trying to attract are going to be further away from the nucleus, so there's going to be less pull, and there's also going to be many more shells as we go down the group, so there's going to be more shielding and less of a pull from the nucleus on any electrons it's pulling towards it. So it makes sense that our best oxidizing agent is going to be small. It's able to get close to any electrons, the nucleus, and it's also going to have few shells to give less shielding. So the oxidizing agents are best at the top of the group. Fluorine is a much better oxidizing agent than chlorine, and chlorine is a stronger oxidizing agent than bromine. So now let's look at the halide ions and how the halide ions can act as reducing agents. So I've quickly drawn the halide ions there. This time they've each got a full outer shell, but as we can see, as we go down the group, we get bigger. So halide ions, they can't act as oxidizing agents. They can't remove electrons from other species, but they can donate electrons. They can give electrons away. So they can act as reducing agents because they can give electrons to other elements and reduce other things. So they can lose electrons. Now, if we consider, we're going to have the opposite effect of what happens when they're oxidizing agents. So to be a good reducing agent, it's going to need to be big, because it's going to be better at losing electrons. So if it's bigger and it's got more shielding, it's going to have less of a pull from the nucleus on the electrons in the outer shell, and that electron is going to be held less tightly, and it's going to take less energy to lose that electron. So our strongest reducing agents are going to be at the bottom of the group. So bromide is going to be a better reducing agent than chloride is, and chloride is going to be a better reducing agent than fluoride is. So just to reiterate, a good reducing agent needs to be large, and it needs to have lots of shielding. So as we can see, they are stronger reducing agents. They get stronger as we go down the group. So I've only shown fluoride, chloride and bromide, but then we'd have iodide and acetate would be even stronger reducing agents. Now, the reaction you need to be familiar with for your exams to show the reducing agents and how the halides behave as reducing agents is the reaction with concentrated sulfuric acid. So if we consider sulfuric acid, the sulfur in it is oxidation state +6. Now, there are many different ways that we can reduce sulfur from being +6. So I can turn sulfuric acid into sulfur dioxide, and the sulfur goes from being +6 to being +4, so it can be reduced a little bit. Okay, if we just finish off that reaction, then I can see that I'm going to need to put 2 waters on the right hand side to balance the oxygens, and then I'm going to need to go back and add in 2 protons, 2 hydrogen ions, and 2 electrons to balance that half equation. Now, if we consider another reaction then, so we could also, if we had a stronger reducing agent, sulfuric acid can get reduced even further. So it can go from +6, but it can go all the way down to sulfur, which is elemental sulfur, which would be oxidation state 0. Now, to do this, we need to balance it again, so we can see that we've got 4 oxygens, so we're going to need to add 4 waters on the right-hand side. And that's going to involve needing 8 hydrogens. I've already got 2, so if I put 6 H pluses, and to balance those 6 hydrogens, H pluses, I'm going to need 6 electrons. So you can see I'm going from +6 to 0, so this is going to take a stronger reducing agent. And finally, if I have an even stronger reducing agent, I can take sulfuric acid and I can turn it into hydrogen sulfide. And from here, our sulfur goes from being +6 to being -2. So balance the equation again, we're going to need 4 waters again, and this time we're going to need 8 H pluses and 8 electrons. So you can see if I've got the strongest reducing agent, then I will end up with hydrogen sulfide, but if I've only got a weak reducing agent, then I'd end up with sulfur dioxide. So the amount of reduction that happens depends on the strength of the reducing agent. So let's look at what happens when we add concentrated sulfuric acid to some different halide ions. So this is sodium chloride. You could equally use potassium chloride because the sodium or the potassium is just spectating, it doesn't actually participate. Now sodium chloride, so the chloride ion would be our weakest reducing agent. So when we add concentrated sulfuric acid to sodium chloride, we get steamy fumes. Okay. Now this is because the sodium chloride reacts with the sulfuric acid and it forms sodium hydrogen sulfate, and hydrogen chloride gas, and those steamy fumes are the hydrogen chloride gas. Now you could test them with indicator strip and you'd be able to see that we had acidic fumes, and that would be how we know we've got the hydrogen chloride gas. Now this is an acid-base reaction. This is not a redox reaction, so there's no change. You can check the oxidation states of everything. There's no change in any oxidation states. It's just an acid-base reaction. So no redox happening here at all. It's because the chloride ion is a very weak reducing agent. It's not strong enough to reduce the sulfuric acid. So let's look at the reaction with sodium bromide. Now, sodium bromide is mid-table, so it's going to be a medium strength reducing agent. So we're going to get steamy fumes again, and we're going to get a similar acid-base reaction to what happened with the sodium chloride. So the sodium bromide will react with the conc sulfuric acid, and it will form sodium hydrogen sulfate and hydrogen bromide. And we could test those steamy fumes with indicator paper again, and we'd see that they were acidic. They'd make the indicator paper go red. But we'd also find that we get some orange-brown fumes as well as the steamy fumes, and this didn't happen last time. And these orange-brown fumes would be bromine being produced. Now, if bromine's being produced, obviously my bromide is changing from bromide to bromine, which means we've got an oxidation state change happening. So bromide is going from being Br minus, so oxidation state of -1, to being bromine elemental, so oxidation state 0. So it's losing 2 electrons, it's being oxidized, and it's acting as a reducing agent. So what's happening to the sulfuric acid? Well, the sulfuric acid is being reduced. So it's gaining those 2 electrons and it's turning into sulfur dioxide. Okay, so there's the half equation for the sulfuric acid reacting and turning into sulfur dioxide. So this is clearly redox, but we've only reduced the sulfur from +6 to +4. So we've only done a little bit of reduction. So finally, let's consider what happens if we use sodium iodide. Now, sodium iodide is quite a long way down, so it's our strongest reducing agent. It's a big atom, it's got lots of shielding, there's not very much attraction from the nucleus to those electrons in the outer shell, so it's easier to lose them. Again, we're going to get steamy fumes, our acid-base reaction, just like we've seen with the other two, where the sodium iodide reacts with the sulfuric acid and forms sodium hydrogen sulfate and hydrogen iodide. And we could test those fumes with indicator paper, and the indicator paper would turn red, showing that we had produced these acidic fumes, hydrogen iodide. That's only an acid-base reaction. There is no change in oxidation state. But you'll see that the tube also goes purple, so we get purple fumes. Now this is because we're forming iodine. So our iodide is turning into iodine. So we're obviously getting redox. We're getting iodine is formed. And although iodine is normally a solid, it sublimes quite easily into a purple gas, and this would be giving it, it's quite an exothermic reaction, it would be giving out quite a lot of heat, so the iodine would be in fume form. We'd also get some sulfur dioxide, as we saw with the sodium bromide, but interestingly, we'd also get a yellow solid formed, showing that our sulfuric acid had formed elemental sulfur, so further reduction. And we'd also get a bad egg smell. Now, I can't show you a bad egg smell in a video, but we get a bad egg smell, and that bad egg smell would be because we get hydrogen sulfide formed. So because sodium iodide is the strongest reducing agent, it is able to take the sulfuric acid through being sulfur dioxide down to sulfur and all the way down to being hydrogen sulfide. So it's able to take it from being oxidation state +6 down to being oxidation state -2 because it's the strongest reducing agent.